Hello friends, in this session we will continue with the discussion on types of heat exchangers. In the first part we have discussed classification of heat exchangers based on nature of heat exchange process and relative direction of fluid flow. In this session we will discuss the remaining two, that is design and constructional features and classification based on physical state of the fluids. The next classification is based on design and constructional features. Based on this, heat exchangers can be classified into concentric tube or double pipe heat exchangers, shell and tube heat exchangers, multiple shell and tube pass heat exchangers, and compact heat exchangers. First one is concentric tube or double pipe heat exchanger. This is also known as tube in tube heat exchanger. As the name indicates, it consists of two concentric or coaxial tubes. Here, one fluid flows through the inner tube and the other fluid flows through the space between the inner and outer tube, that is the annular space between these tubes. Due course of the flow, heat transfer takes place from hot fluid to cold fluid through the wall material of the inner tube. Depending on the flow arrangement and flow direction of the fluids, it can be parallel flow or counterflow type. The next classification based on design and constructional features is shell and tube heat exchangers. Shell and tube heat exchanger is a common type of heat exchanger in industrial applications. It consists of a bundle of parallel tubes enclosed in a large shell. Main parts of the heat exchanger are a shell, bundle of parallel tubes, tube inlet and tube outlet for tube fluid, shell inlet and shell outlet for shell fluid, baffles, headers on both ends, and tube plate. Tubes in the heat exchanger is secured at the end to a plate known as tube plate. These tube plates consist of a number of holes where the ends of the tubes are attached or supported. These blue elements are baffles and they are provided at regular intervals along the length of the tubes. This entire tube assembly is now enclosed in a shell with another tube plate at the other end. This image shows the view of tube bundles enclosed in the shell. Two enlarged portions known as headers are attached at the ends of this structure. Here we can see headers at both ends. One front header, two rear header. In a shell and tube heat exchanger there are two fluids. One shell fluid that flows through the shell and second the tube fluid which flows through the tube. The tube fluid enters into the tube from the front header, flows through the tube, and at the exit of the tube, fluid is collected and taken out from the rear header. Thus, these headers act as reservoirs to receive tube fluid at the inlet and exit sides of the tube bundles. Tube fluid enters through the tube inlet, flows through the tube, and exits through tube outlet. Shell fluid flows through the shell over the tube surfaces in counterflow pattern. Consequently, heat transfer takes place between the shell fluid and the tube fluid through the tube wall. Here baffles are used to ensure uniform spacing of the tubes inside the shell. Baffles also help to direct the shell fluid in such a path so that shell fluid can make maximum contact with the tube surfaces and thereby enhances the heat transfer between the fluids. In addition to this, baffles can induce turbulence and enhance mixing of shell fluid. They also physically support the tubes and minimizes flow-induced vibrations in the tube. These are the points pertaining to shell and tube heat exchanger that we have discussed. Normally, shell and tube heat exchangers are suitable for large capacity applications, so they are preferred in industries. As they are heavier and bulkier, they are not preferred in automotive and aircraft applications. Here we can see shell, baffles, tubes, and tube plates associated with a shell and tube heat exchanger. Next is multiple shell and tube pass heat exchanger. In a shell and tube heat exchanger, both shell and tube fluids pass only once through the heat exchanger. As both the fluids pass only once through the entire length of the heat exchanger, they are also known as one shell pass and one tube pass shell and tube heat exchangers. But if our heat transfer requirement is more, then we will reroute and force the fluids to flow back and forth through the heat exchanger. This is done to enhance heat transfer. This rerouting can be done on shell fluid or tube fluid or on both the fluids. Such a shell and tube heat exchanger with more than one pass of fluids are known as multi-shell and tube pass heat exchanger. Here we will discuss two variants of multiple shell and two pass heat exchanger. They are one shell pass and two tube passes and two shell passes and four tube passes. Here shell fluid passes only once through the heat exchanger represented by red color, whereas tube fluid represented in blue is rerouted and made to pass twice through the heat exchanger. So here we have only one pass of shell fluid and two passes of the tube fluid. So this is known as one shell pass and two tube passes type heat exchanger. So this is known as one shell pass and two tube pass type heat exchanger. In the 3D view, it looks like this. Yellow arrow represents the flow of tube fluid and red arrow represents shell fluid. Here we can see that tube fluid enters through one of the headers and passed twice through the length of the heat exchanger and moved out, whereas shell fluid makes only one pass. Here we can also see that how baffles direct shell fluid to flow over the tubes in a heat exchanger. In the next configuration, both shell and tube fluids are rerouted. Shell fluid is made to pass twice, whereas tube fluid executes 4 passes. Hence, this is known as 2 shell pass and 4 tube pass type heat exchanger. In all these configurations, shell and tube fluids move in counter flow pattern. Next is compact heat exchangers. Compact heat exchangers are special variants which are designed to provide large heat transfer area per unit volume of the heat exchanger. This large heat transfer area is achieved by attaching closely spaced fins to the surface that separates the two fluids. Here we can see a large number of fins attached to the tubes that separates the two fluids. You may probably know that providing fins increases heat transfer area. The ratio of heat transfer surface area to volume of a heat exchanger is basically known as area density, and it is denoted by beta. A heat exchanger is categorized as compact heat exchanger if area density beta is greater than 700 meter square per meter cube. Compact heat exchangers are preferred when at least one of the fluids involved in heat exchange is a gas. We know that gases have inferior thermal properties compared to that of liquids. Consequently, heat transfer coefficient associated with the gas flow will be low. This is compensated by providing more surface area in the form of fins. Compact heat exchangers are used in applications where there is strict limitation on weight and volume of the heat exchanger. The next classification is based on physical state of the fluid in the heat exchanger. So far we have discussed heat exchangers with fluids in single phase. Here we will deal with heat exchangers associated with phase change. The point is, whenever a fluid is subjected to phase change, its temperature remains constant. Phase change heat exchangers can be broadly classified into condensers and boilers or evaporators. Here we have a condenser with water as the cold fluid and steam as the hot fluid. Cooling water is used to condense steam at 40 degrees Celsius to water at 40 degrees Celsius. Consequently, the cooling water temperature increases. Here hot fluid has undergone phase change at same temperature. So in a condenser, hot fluid undergoes condensation or phase change and its temperature remains constant. On the other hand, for boilers and evaporators, the condition is just opposite. In the boiler shown, water is the cold fluid and hot gas used to boil water is the hot fluid. Water takes latent heat from hot gas and evaporates at same temperature. So, in a boiler or evaporator, cold fluid undergoes phase change at constant temperature. Now we know that in a condenser, hot fluid undergoes phase change and its temperature remains constant. So, in the temperature profile, hot fluid temperature will be constant and cold fluid temperature increases as it takes heat from the hot fluid. Whereas in the case of a boiler or evaporator, cold fluid undergoes phase change, so the temperature of cold fluid will be constant. Whereas hot fluid temperature decreases as it loses heat to the cold fluid. That is all about this session. Thank you for listening. We'll meet in the next session. Till then, bye.